Okay, I apologize. The video decided to stop on me for a minute right in the middle of what I was doing. So what we were saying is that the logarithmic function has a domain 0 to infinity. So remember, domain is the input or x. So that means that when we are using logs, the x or the input value has to be positive. This is going to come up more when we look at solving equations that have logarithms in, similar to what we did when we had to check our solutions before to make sure they satisfied the original equation or the domain. We'll have to do that here too. So things like having log base 2 of 0 or log base 3 of -1, those are things that do not exist. You can only have numbers here that are positive. And if you tried to enter those into a calculator, which a calculator won't do log base 2 or log base 3, but if you did try to do those, you would see that you get a domain error. Alright, so this next couple of problems is just to illustrate those properties that we just looked at. So this first one is illustrating property 1. You see it looks like the log a1 equals 0. So as soon as I see log 6 1, I can just write equals 0 due to that property. But to show you why it's true, if I have log base 6 1 and I wrote the equals x like we did before, if we do the e, we'd get 6 to the x equals 1. So what this is asking is what power I can raise 6 to and get 1. And of course there's only one number that you can raise something to and get 1, and that number is 0. The second one is illustrating property 2, and that's when the base and the number are exactly the same, and you see property 2 tells me that that answer is 1. So just to illustrate why that's true, if we wrote it out, we would get 5 to the x equals 5. And of course this is to the first, and because those bases are the same, we could drop them and we'd get x equal to 1. So anytime the base and the number are the same, we know we're going to get an answer of 1. And if we have a base and the number is 1, we know we're going to get 0. Okay? So the last thing that we're going to look at with these is it's always kind of nice to be able to visualize what these functions look like. So we're going to stick to pretty much the basic graphs. I'm not going to be shifting them around, giving you lots of different things. We're going to stick to these two basic types. So remember, the function notation, as always, is just another way to write y equals 2 to the x. So we need to choose some values for x to plug in. And you can really choose absolutely anything you want to. Again, this one is going to kind of come down to if you've probably heard people say things like that grew exponentially, or those kind of statements means that it grows pretty fast and pretty quickly. And exponentials do have that trait, so to keep them on our coordinate plane, we're going to want to keep the numbers within a smaller range. We do want to use 5 values for x here. So normally we're just going to pick -2, -1, 0, 1, and 2, just to try and keep this exponential within range, okay? So then if we plug these in, we're going to raise 2 to the -2 power. Of course, you can put that into your calculator, but we know that negative exponent is going to take the reciprocal, so it's going to be 1 over 2 squared, which is 1/4. And if you prefer with graphing, you can use your calculator also. 1/4 is the same thing as 0.25, if that helps you to estimate when you graph. Then we just repeat that process. If x is -1, we get 2 to the -1, which is going to be 1/2. Or you could write it as a decimal. If x is 0, any number raised to the 0 power is 1. If x is 1, we get 2 to the first power is 2. And if we use 2, we get 2 to the second power, which is 4. So what I generally do with these last 3 are what I call nicer numbers. So I generally graph those first to try and get an idea of the shape of my graph. So I've got 0, 1. Then we have 1, 2. And then we have 2, 4. And then if I go back to the other ones at -1, it says y is 0.5. So that means I'm going to go about halfway, right? And then at -2, we're at -0.25, which is a little closer than that one. And what you'll find happens with these is they're going to get closer and closer and closer to that x-axis, but they're never going to touch. So we want to kind of swoop down through the points, and it's going to come towards that x-axis but never touch. All right.